Okay. Um, so this also leads. So this has two problems. It leads to like a really big key, but also a very slow signing process. It's not that it's impossible to sign. It's that you have to try a certain number of times. This is still a toy example, but if you have to try many times, it means that the signing process is very slow. And so when you compare with other um, signature scheme, for example, with full domain hash, you get something like the signing time is in the order of like 9 milliseconds. And for the similar level of security, CFS would take something like 10 seconds. Okay, so obviously extremely slower. There are some good features to it, but in the end, like you cannot fix this. It's an approach that is not optimal. Okay, the underlying problem is exactly that it doesn't cover the full domain. So now you understand also what's the meaning of the full domain hash. Right? Full domain hash means that whatever you get out of the hash is going to work. Here, whatever you get out of the hash, you have no way to predict to map into like a decodable syndrome. Okay, you can just like try to hit at random, and then like you can choose your code parameters so that you have like a better coverage or whatever. But like it's not ideal in principle. Okay, so let's move on then, and then let's talk about. So if this was the only way, essentially, if hash and sign was the only way of doing things, we would be a little bit short of resources. But here's why we start talking about identification schemes. Okay, and here is important because this is, if you want, like a third type of cryptographic primitive. Now we've seen encryption, we've seen signatures. What is an identification scheme? Okay, so an identification scheme is a protocol between two parties, a prover and a verifier, right? So it's again a means of authentication, but it's interactive, right? It's interactive. And the goal is, if you want even more intuitive, is like trying to convince the verifier that you know something, that you know the certain knowledge of a secret.
Without telling them.
Without telling. And in fact, thanks, Misha, this is a good prompt. Like essentially, this identification scheme have to be ZK, which stands for zero knowledge. So sometimes these are also called like zero knowledge proofs. For example, because the verifier cannot learn anything about your secret other than you actually know the secret. Okay, so it looks like a very challenging task. Essentially, you have some public data always, D, which could be, I don't know, the group in which you're working or something like this, right? And then you will have a secret S. You can think this is like a secret key, and then like a public key. And you're trying to convince the verifier that you know S. Okay, so there's actually more than one way to do this. The simplest way, and I like to look at it as really as a table because it's interactive and it's easy to visualize. Essentially, what you do, the first thing is you do a commitment step, and you usually, for example, choose some sort of random object, right, and commit a certain function which should be hard to invert. Let's call this capital Y. And so you then send this to the verifier. Typically, this is the same that you use to generate the public key, for example. So it's kind of like an ephemeral instance of your secret public key thing. Okay, so if you imagine the S gets transformed into the public key, this is kind of like the same function, but on like a random object. Okay. Then the verifier sends what is called a challenge. So C, challenge is chosen at random in a certain challenge space. Okay, and again, this depends on the scheme. And so you have a challenge step. And then the verifier, the prover, at this point, so By committing, what you do is that you fix something so you cannot cheat later. Okay? Because otherwise it would be easy to just like receive something from the verifier and then like adapt your response to it. So you kind of pre-commit to something.
Okay.
You know? And you're like, oh look, I know how to solve this. Okay, take this challenge and solve this particular instance. Okay, and then like the prover actually computes a response z, which is going to be a function of the secret, the challenge, and the commitment. Okay, so it has to take into account everything. And we said that the scheme has to be zero knowledge. So once you send the response to the verifier uses the public key, essentially, and the public data, and the commitment. So all the public information, right? So the commitment is what you sent him, public data and the public key were fixed up there to verify that Z is correct, and then output accept, reject. Okay. So it's a kind of like it's an interactive proof of knowledge, how they call it, right? Or it's a zero knowledge proof of knowledge. Okay. There are several kind of like equivalent names for it, and this is like at the base of an identification scheme. Okay. If you want the proof of knowledge, is like the underlying matrix, and then the identification scheme is what you do with this proof of knowledge. Okay. And now this looks very abstract, of course, like when we describe the first like skeleton of the public key encryption scheme or a public key signature scheme, but you will see with some practical example what this does. Okay, so in the end, what the verifier should acknowledge that you do know the secret, but will not learn the secret or impart the secret. It should be really zero knowledge. If there is even like a little bit of knowledge, then that exposes your secret, right? And that's not good. So here is how you can do a couple of examples, and then like we'll see why we care about identification schemes. Okay, so so the first simplest thing that you can think of is, say, discrete logarithm based. Okay, so in this case, what you can do is you can set the public data to be like G, which is your group element, and then you choose your secret exponent S. So this is like mod P, whatever. So you're working in like FP, and you can imagine that this is like order Q, okay, as the usual setting that we saw. Okay, so G doesn't need to be an entire primitive root, but maybe it's like something smaller. Then the secret S is something like mod Q minus 1. Okay, it's an exponent. And then your public key will be G to the S. Okay, let's call it like X. Cool. So that's kind of like the standard public key cryptography based on this logarithm setting. Now what do? We said, okay, the prover and the verifier are communicating. The prover is kind of going to do an ephemeral instance. So we'll choose like another exponent T at random, right? Again, like mod Q minus 1, and then compute G to the T. Let's call this Y. Okay, so the notation is, so you see in this case my function is the same as the public key one. Yes. Then I'll send this Y to the verifier. The verifier will choose a challenge. In this case, I can think this is B as a bit. So we'll just choose even a bit. And send B. And basically B, in this case, because it's binary, this is a very simple instance, this one, right? But depending on what B is, you can imagine that, so if B is 0, you reply with T, and if B is 1, you reply with S inverse T. Okay, this is going to be a certain response R that you send over. Okay. You can even formulate it if you want to, like S inverse to the V minus 1 or whatever. And so, yeah, so then what you do to verify essentially is you take the response, and if B was equal to 0, then you check that G to the R is equal to A to Y. Okay? And in this case, it's kind of trivial because the R is going to be T, so you do G to the T, and it's exactly Y. And if B is equal to 1, you check that G, not G, but you're going to have to use your public key, so X to the R is equal to Y. Okay? And this is because X to the R is in fact G to the S to the R, which is G to the S, S inverse T, and this is again G to the T, which is Y. Okay? So in this particular type of zero knowledge proof, your challenge is just a bit, and you either send a dummy instance or the one that actually contains the private key, right? Because clearly in the case B equals 0, you're just sending T, and in the other case you're sending S inverse T, which contains your secret S. So you really kind of verify properly that you know the secret in the second challenge. But if you only asked the second challenge, then it would be easy to extrapolate the secret. The tricky thing is being able to respond to both. Okay, so it's easy to see that, and this is a delta.
Easy to extrapolate the secret?
Huh?
If you only ask the second task?
If you ask the second task, the problem is, if you ask just the second one, there is no challenge, right? So you just know what to reply. So what you can do is choose a random value here, R, right? And then compute X to the R, X is public, and then set that as a commitment. So even before receiving the challenge, you can already like pre-prepare yourself for answering correctly, right? Without knowing the private key, this S inverse T is a product of two integers, and so it looks random. So it's clearly zero knowledge, but you can forge it, right? The really hard thing is so yeah, obviously the case B equals 0, anyone can forge because it's just T. So what you do is you just choose G to the T equal Y, send that, and then when he asks, you send T. Okay, there's no secret there. Or you could forge the other one by choosing a random R, setting up X to the R equal Y, and then when he asks you, you send R. But what you cannot do is know both. Because if you know both, right, it means that you actually know, so that you actually know how to create these two exponents, which means that you actually have to know S. Okay? If you're able to provide two responses such that G to the R1 is equal to X to the R2, because they both have to be equal to the commitment, right? Mm-hmm. Then obviously this is the same as G to the S R2, right? And this is mean that R1 is to be equal to S R2, well, modulo P minus 1, whatever, Q minus 1. And therefore, you can easily get S as R1, R2 inverse. So you see, if you were able to answer both, then you can solve discrete logarithm, essentially. And this is at this point, typical kind of reverse proof that we saw in a lot of situations, like, oh, if I break this, then I'm able to solve this hard problem. So obviously, I cannot do this. So you see what the problem is. So the trick is, you cannot simultaneously answer both challenges 0 and 1. And even though it looks like the first one is dummy, there's no secret there, well, B is chosen at random. So half of the times, you will ask 0, half of the times you will ask 1. And you don't know, right? If you knew that he was going to ask 1 more often than 0, or he's only going to ask 1, then you can always forge that with a certain important probability, right? But in general, if B is chosen at random, then you have a probability equal to 1/2 of being asked 0, a probability equal to 1/2 of being asked 1. And so the best you can do is you can prepare for 1, you can hope that he asks for 0, prepare for 0, and if he asks 0, you manage to forge. And if you ask for 1, then you lose, okay? So it is not an entirely satisfactory protocol, of course, because this leads to a certain cheating probability, which is technically also known as soundness error, because soundness is the property that tells you that you always get verified correctly. So an honest verifier knows S, so he can answer always both challenges. Honest prover. A dishonest prover can only answer challenges with probability 1/2. So you have this discrepancy. So that's why it's called soundness error. But you can think really in terms, if you think this is a game, like, okay, it's cheating probability is an acceptable term. So the adversary can cheat with probability 1/2, which means that, of course, to be authenticated correctly, what do? You have to repeat this several times, right? So if you do several independent executions of the protocol, right? So what you do is you then repeat. For example, like gamma times. Well, then every time the adversary has a 1/2 probability of cheating, right? But these are all independent, so basic probability counting tells you that essentially you get a 1/2 to the gamma, which is 1/2 to the gamma, which is 2 to the minus gamma. And so you just set gamma to be whatever level you want of authentication. So gamma can be typically, I don't know, 16 or 80 or 128, okay? So you repeat the process several times, and then at this point you're like, okay, if someone answers every single time correctly, then I'm pretty sure up to this degree of confidence is that's like an honest prover.
Don't you need to just answer both of them once?
No, because every time you change, right? I'm saying it's like independent executions.
Sure, but if you've answered both task 1 and task 2, since you didn't change the X.
No, but you're changing the ephemeral one. This is ephemeral. Every time you choose a different T.
Yes, but X doesn't change.
Yeah?
And so if you chose a different T, you wouldn't be able to preset X in such a way that you would know challenge 2.
No, X is public key. So you cannot touch that at that point. You're trying to impersonate the prover. You're not setting X. X is given, verifier as X.
Isn't that how you solve task 2?
No, I mean the task 2 would basically correspond to like knowing the S such that
you just said Y was X.
Yes. Yeah. X is the public key. Okay. Public key is set. Of course, if you're able to choose your own public key, then you're essentially an honest guy. You know.
Because of the commit. Okay.
Okay. So the commitment exactly like serves the purpose of like setting things in stone. You have to commit before you receive the challenge. Right. And the challenge kind of sets what kind of response the guy is going to expect. Okay. And so there is this idea that there is a certain cheating probability which is non-zero. And you can just repeat the protocol, and then like it's independent execution, so it's 1/2 times 1/2 times 1/2, which leads to like as high an authentication level as you want. Okay. Obviously, if you repeat the protocol 128 times, then you're pretty sure that is an honest guy. Okay. So you only accept if the verifier would accept every time. Okay. Does it make sense? It's a different approach, right? But it's interesting. And okay, so why do we care? I mean, we'll go a little bit back and forth. Why do we care about zero knowledge? First of all, I mean, this is cool that you can authenticate yourself without revealing your secrets. Also, this commitment is usually a hash. So what you can do is you then compute like the hash of y. Right, and call it H. And here you send H really, rather than Y. Because you see that in the end you use this Y just as a comparison term. Yeah. So here you can just check H, and here you just compute this and then take the hash off. Okay. So this helps because you cannot for example, if you see why you could try to like reverse engineer things, right? And in this case, it's protected by this logarithm problem, but in some other cases, it may be easier. But also, in terms of communication, hash value is usually a short string, 128 bits, 256 bits, which is, for example, much shorter than a modulus integer. And if this was just one round, maybe the difference would not be that big. But if this is several rounds, then of course your communication will increase proportionally, right? So in the end, and we will get to this in a point, but if you have to authenticate yourself by doing several repetitions, you're communicating many times. And you're sending this is your communication tape, over and over again. It's not the 1 bit here, right? That makes a difference. This you can't do much about, but if you can shorten this from 1,000 bits to 256 bits, each time you repeat the protocol, then it's meaningful. Okay, so you use a hash for security, you use a hash for compactness, for practical instance, but also you use a hash, and this is where it gets interesting, to transform, because this is an interactive protocol, but we can make it non-interactive. So we can transform it into a non-interactive protocol via a transformation which is due to Fiat and Shamir. And yes, this is the same Shamir of RSA. He's an incredibly clever guy. And so he was studying secret sharing schemes, identification, also different stuff back in the day. So the transformation is very simple. Suppose that you have an identification scheme I that does, for example, the 3-pass thing. Some schemes do 5 passes. They do commit, challenge, response. Okay, so any identification scheme can be turned in this way. When so you want to now turn this into, if it's not interactive, what is it? It's a signature scheme. Because the signature is the same thing, you authenticate yourself, but you're not allowed to communicate with the guy and get the challenge, right? So what you can do is basically, you can do the commitment normally. So you take now a message as an input, right? That was not part of the identification scheme before. In the identification scheme before, you only had the secret. There was no message to begin with. But now you take a message on top of the secret S. And what you do with that? Well, the commitment, you can do it like normally, but then you have no way of receiving the challenge because you're not going to ask a challenge to the guy that you're signing from, right? So what you do is instead you generate the challenge as a hash of your commitment, right, and your message. So you can do because the challenge is supposed to be random anyway, right? So what you do is you compute it as a hash function of your commitment. So you generate your random commitment instance, and then you put it together with the message and hash it, and that will give you a random value in the correct domain. And then you will compute the response Z, and your signature will then contain the commitment and the response. Okay, so we're going through this, right? Basically, you do commit, you generate the challenge yourself, compute the response, and then send all that as signature. But so you're kind of like doing these steps all as a signer, because it has to be non-interactive. And then the verifier will just do this bit. Essentially, will verify as in the identification scheme. So this is the signing process, and the verify algorithm of the verifier. It will just take a message and signature pair, like in any signature scheme, right? And then the signature, remember, contains the commitment. So the signature will be a Y and Z pair, right? So then you will compute a challenge C as hash of Y and a message, right? And then verify Z as in the identification scheme. Because now you have the challenge, the response, right? The commitment, everything that you can.
And since the commitment goes in the hash, it makes it very hard to change it based on the challenge
Exactly.
that you get.
Exactly. You lock it in. You lock it in with the hash. Okay. So it's a clever transformation. Basically, the key idea is that you're going to challenge yourself by committing to a hash value, by using a hash value, which depends on your commitment in the message. And the verifier is able to like regenerate that challenge. You don't have to pass the challenge because you're giving the commitment and the message. Right? And so you can basically with this, and there is a very important proof that this is secure. So you can take an identification scheme that is secure against impersonation up to the desired level, right? And it turns it into a, remember that we discussed UFCMA, which is existential unforgeability in the CMA attack. So you can obtain a strong signature scheme by just taking an identification scheme and then like making it automatic. So this is a path to creating signature schemes. Of course, the caveat is that you're going to have to give the Y and Z as signature, right? So if your identification scheme is error 1/2, then you have to do it several times, and then you need the whole transcript as signature. Make sense? It's not just one Y and one Z, but it's going to be that for each round that you do. So the soundness error is a bit of an annoying problem because you have to repeat the protocol several times, and the signature will end up being very long. It's not necessarily slow, as in like other instances that we saw, for example, for CFS scheme, but it will get long signatures. Okay, so here is an example. So this is an important paradigm to keep in mind with discrete logarithms, and then we can see that we can do better as well. Okay, but let me make an example that is code-based. The first scheme. So why we care about identification scheme? Because we can turn them into signatures. Besides, identification scheme themselves, signatures are a desirable primitive. So what happens in the code-based realm? Okay, in the code-based realm, we have this scheme where the public data consists of parity check matrix H. Okay, and then the parameters for the code N, K, W, the usual stuff. Yes? Okay. The secret key, you can imagine, is the typical secret in all of the code-based schemes is the error, essentially. Right? Is what because again, you want to base it on the hardness of the coding, right? So you're going to take this in like F2 to the N, but like a weight W, right? Low weight, because otherwise, again, it's just an algebra problem, right? But if it's low weight, then it's a hard problem. I think we discussed this. And then your public key, let's call it big S, is like syndrome of that. Okay? So again, we're kind of setting up for like a neither writer sort of thing. Is the basis, even Maclise we can think is basically the same as the syndrome coding problem, right? We just use the generator metrics instead, but the secret, the hard part is always recovering the error. Whether it's the error from a syndrome or from a noisy code word, it doesn't matter, it's the same thing. Okay? So you want to use syndrome coding. Now the good thing is, this is completely a random matrix, because you're not going to decode this error. In fact, you don't want anyone to decode this error, but you want to prove that you know it. So there is an advantage in this, is that you're not using any trapdoor. Like you didn't for the previous scheme. You're just showing that you know a certain secret exponent. To figure out that exponent, you have to solve discrete logarithm, right? It's the same thing here. You're trying to prove that you know a certain low weight vector. If you were to break that, you would have to solve syndrome decoding. Okay? So the advantage of this identification scheme is they use purely random instances. There is no trapdoor here. And this is why it became of interest, because if you try to use the trapdoor, then you're doing the hash and sign thing. Right? So how can I do this? This protocol by Stern is actually even more impractical because it is 3 pass, but it's a little bit more convoluted. So what you do is then you choose for your commitment step a random vector in F2 to the N. Yes. Again, this kind of like looks like a another dummy instance, but you also choose a permutation pi. Okay, and then you set 3 commitments, not just one. You set C1, C2, and C3. And C1 is going to be a hash of pi and the syndrome of y. Okay, so you're not just committing the syndrome of y. That would be easy because by itself, it would be easy to forge. Y is not restricted to be any specific low weight. Then here you can commit instead the hash of the permuted version of y, and here you're committing the hash of the permuted version of y plus s. And you see I'm already using hashes because we said there's no point sending the actual stuff because we always use the commitments to just check. So you send these 3 commitments, C1, C2, and C3, to the verifier. This is the prover guy. The verifier will send back a challenge, but in this case is just not a bit, but it's like a treat, or like 0, 1, 2. And essentially, now you see you've got 3 commitments. With each choice, you verify 2 out of 3 of them. For example, if b is equal to 0, you set your response to be, what can you reveal safely, y and pi? So this is always like the dummy instance. If b is equal to 1, you reply with instead y plus s and pi. And if b is equal to 2, you set your response to pi of y, pi of s. Okay? And notice that, okay, this is purely random stuff, so it's clearly zero knowledge. This is a random permutation, and you send y plus s. Now, the point is that s is low weight, but y is full weight, potentially, is chosen at random, so it completely hides the s. It's kind of like if we're doing a one-time tile on top of it. Okay? This is why we cannot choose y to be low weight, because if I have something low weight and something else low weight, it's not going to hide it very well. There's still going to be a lot of zeros left. Okay? Here instead, you are giving pi of y, all random, and pi of s, but you're not giving pi itself. So if you send pi of s, what do you learn about the secret? Nothing, because pi of s is just going to be a permuted version of the vector, so it has the same weight, but you already knew the weight already. So that's not going to tell you, I mean, it could be anything, right? You know, once you know that a vector has a certain weight, it's a binary vector, it's just got a bunch of ones, well, it could be a permutation of anything else. So the only thing you can try there is like try all possible permutations, see if there's something that makes sense, right? Well, that's not very practical. Obviously, you know, permutations is factorial, so if you were to try all possible permutations and see which one of them gives you the private key, the public key, you know, then obviously that would be taking forever. So what can you check with this? With this, you can check C1, because clearly I give you 1 pi, you check pi and h times y. And you can also check C2, because they give you pi and y plus s. What you can do is that you can use y plus s, compute the syndrome, subtract this, right? And that will be pi of y. Yes, you can do that, I think. Yes. And then with this, you can check C1 and C3. Sorry, yes, no, yeah, of course, this is y and pi, yes. So I was looking at the wrong row, yes. So C1, you can check because it's pi and syndrome of y, and C2 you can check because you can just do pi of y, right, of course. Here you check C1 and C3. Again, C1 you can check because pi is going to be pi, and then y plus s, that's what I was saying before, you do h times this, and subtract the public key, and that's going to be h times y. Okay? And then C3 you can check because it's pi of y plus s. And then here, obviously, you can check C2 and C3. With pi of y and pi of s, you can do pi of y plus s, just summing them, permutation are transitive, and you can just check C2, that's just pi of y. You don't need the pi of s. Okay, so you can check any two, depending on what the answer is. Okay. You also have to check here that the weight of pi of s is the correct one. Otherwise, it would be easy to forge. Okay. So this is like a similar scheme to before. But so an honest prover is also always accepted. But someone that wants to forge can do something similar to before. Remember, before we had two instances. I can either prepare for the 0 or prepare for the 1. And that gives me a 1/2 cheating. And here actually it's worse, because what you can do is not only prepare for one of the three, but you can actually solve two of them at the same time, right? So you can, for example, try to satisfy the 0 and the 1, right? And I will show you just one of them, and that hopefully should convince you that it works. So suppose that you're trying to respond in the case 0, yes, and in the case 1. Then what you need is a permutation, a random vector here, and another random looking vector here. So what you do is you choose y and pi properly at random, right? And then you choose like x at random of weight w. So this x should replace the s in your intentions. Yes? And then what you can do is you can build C1 and C2 normally, because all you need is pi and y, and this you can do honestly. And here you will need pi of y plus s. So instead what you do, you just build okay, so yeah, so and then C3 is going to be the hash of I lost the row, pi of y plus x. So instead of doing pi of y plus s, you don't know s, you just choose another vector that works the same weight and set C3 to be that. Okay. And so now, if b is equal to 0, you can easily reply with y and pi, because you've got y and pi. If b is equal to 2, right, what you can do is you reply with pi of y and pi of x, and that satisfies the thing, right? Because here you get pi of y plus x, which is that, right? And that had the correct weight, choose the correct weight. And then you also want to verify C2, which is pi of y, or you send pi of y. Right? So what you cannot verify is the bit 1. So if b is equal to 1, you fail, because in that you would have had to send y plus x and then check the syndrome, remember? But that syndrome is not going to be the same syndrome because this x is not the same as s. So you can fool the verifier in 2 out of 3 cases. With this strategy, you can answer 0 and 2, but not 1. And the problem here is that 0 and 2 only depend on having a permutation, this random vector, and a low weight vector. And you're sending pi of s, so instead of pi of s, you send pi of another vector with a low weight, it's going to work. But what you cannot verify is the syndrome, because here to check the remaining one, you would have to use the public key, what is the correct syndrome, right? So you can then change strategy and prepare to answer 0 and 1, right? Or 1 and 2. But in the end, you always have a 2/3 cheating probability. You can never answer all 3, but you can answer the first and second, the first and third, the second and third. So long story short, 2/3 means that you have to do even more rounds to achieve the same authentication level. And then the signature is very long. With stupid parameters, it's something like 150 kilobytes. With better parameters, it's something like 60 kilobytes, give or take. But you see, like the point is that every turn, these commitments are all hash values, so they are short. But your answers, every time you send a vector, y plus s, right? That's a length n vector binary, so that's n bits. N bits, n bits, n bits, n bits, that's long. Right? So the signatures become really, really long. These schemes can be tweaked and improved, and the soundness error can be reduced. So you can do code-based schemes that have soundness error of 1/2, and you need less rounds. They can be more compact, but still like they end up with like a somewhat big signature. So this is not an ideal solution, and for this reason, it would be better. What is the problem? Is this standard error is a problem because you have to repeat to authenticate many times. If my challenge space was bigger, then obviously I need to repeat fewer times, right? So now let's see how we can do this with better technique, which unfortunately kind of doesn't really work all the time. So this technique is due to Schnorr. And when you transform this into a signature scheme, then it becomes the very famous Schnorr signature scheme, which is used all the time. And so the identification scheme at the base of it is very simple. It goes like this, essentially. So the setup is going to be the same, right? So here we have a prover and a verifier, and we have public data D, which is going to be basically G and the mod P and the setting Q, right? All the usual stuff. And then what you're going to do is your secret key is going to be so is S, and then this is your secret, and then you just compute G to the S. Let's call this like X again, right? And it's going to be your public key. So same thing. Now let's try to do it properly. Here we compute a T at random, compute G to the T, and let's call this Y, right? So it's again an ephemeral instance, and then you send this Y to Bob, or the hash of, doesn't matter. Bob will send the challenge as C, and now we want this to be an integer rather than a bit. So we'll take this like in, for example, like 0, 2 to the T minus 1, something like this. And then basically, yeah, T is like the bit length of this challenge, typically 160 or something like this, so it provides a high authentication level. Okay? And then Alice computes the response, or the prover anyway compute the response, as T minus CS. Okay? So this T minus CS lives again in the integer realm, and it's something that you can typically do because you're working with integers, and there's the duality, remember, between exponents and integers that discrete logarithm schemes really exploit very well. So you send the T over, and then the verifier computes and check. So it will use the public information, and you want to be equal to Y, right? Because that's your commitment. How do you get to Y? You compute G to the Z times your public key X to the C. Okay? And this should work because G to the Z is G to the T minus CS times X, which is G to the S to the C. You see this gives CS, cancels out, you get G to the T, which was exactly Y. Okay? Now you can do, this is a hash value, and you just hash this stuff. And it's the same thing. And then you can apply Fiat-Shamir, and this becomes a signature. Okay? Now this is an even simpler 3-pass protocol, and to cheat, you actually have to guess C. In the exact C, right? If you were able to guess the C, then you can build such a response. Right? Because you can essentially, if you're able to get the C, you can again get some random stuff here, pre-prepare your answer, and commit to that. Right? Okay. But if you don't know the C, then you would essentially have to solve the discrete logarithm problem again.
Okay.
Hopefully you don't have to go through the exact proof, but you can see why, right? It's a good exercise for you to see, like, okay, what can I do? Suppose I choose, because that's how we impersonate, right? If you try to impersonate, you don't know what the challenge is going to be, so you have to like pre-prepare things and hope that they work. So start from the response, and then suppose that you guess the C, how can you form the T, right? And then if everything passes the verification, then you manage to forge. But you have to guess the exact C. To guess the exact C, you have 1 in 2 to the T chances, so that provides a very high authentication level, right?
Yeah.
You don't need to repeat this, for example, if your T is already like 160 or something. Cool. So this is like a much more clever scheme, and again, it becomes very efficient when you do it because you have to do it only the one time. And the problem with the Schnorr scheme is that, unfortunately, it is based on discrete logarithms. So if we are having an eye towards post-quantum signatures, then we have to, obviously we cannot use this. But it does gives us an insight in what could be an efficient way to do signatures. First of all, we know that identification schemes are viable. And then if we can do it in this way, well, then maybe, it starts to actually look interesting. And it turns out that this works very well for lattices, much better than, for example, than GGH signatures. And let's see how we can translate this to the lattice case. And I think you will find this interesting. Okay, so so let's see how we can translate this to lattices. In the lattice case, this was investigated by Lubashevsky. In really recent times, 2009 is the first time that something like this appeared. And it was quite a sensation because, again, up to that point, people were always thinking like, okay, we're doing stuff with trapdoors. And so Lubashevsky's paper was called Lattice Signatures Without Trapdoors, essentially. And that's really the title of the paper. Okay, and so it's like, okay, we can use the identification scheme technique that works so well, for example, for Schnorr, in the lattice realm as well. And of course, there are some subtleties that I will point to, but remember that the scheme has to be zero knowledge, so I'm skipping some steps here, right? But the scheme has to be zero knowledge. So if you're sending, one example, in the Stern scheme, you can easily prove that this stuff is zero knowledge because you're either sending like entirely random stuff. The only thing that you have to be careful with is pi of s. Well, that's not going to reveal anything because it just tells you the weight of the vector, which you knew already. Permutation is a well-known invariant for the Hamming weight, obviously. And y plus s. Y plus s, because y is chosen uniformly at random, you're putting a random distribution on top of s, it covers it. So in this case, it's kind of like easy to believe. And that's the advantage with these cheating schemes, if you want, advantage, so to say, is that it's easy to believe the zero knowledge. It's easy to prove. You never have to believe, you have to prove the zero knowledge.
Yeah.
But it's easy to prove because you just say like, oh, I take a permutation, I put it on top of a vector, like, okay, that destroys completely the thing, right? In the simple 1/2 scheme that we had before, it was easy. Now you have to kind of show that this thing actually looks random, that doesn't leak anything about the secret. This is maybe a little bit more elaborate, okay? And in fact, for the lattice-based, what happens is that your public data will be like all the setup for the lattice, the dimension, and blah, blah, blah. And then you're going to choose as your secret in a certain distribution of length m. So this, because remember, the lattice is all about the size of these things. So the coefficients of s will be small in a certain interval given by ds. Okay, and then you are going to essentially compute the public key, big S, and essentially we are choosing a lattice vector where well, okay, it's a little bit more complicated, but essentially you're putting in a lattice vector. Lattice vectors are defined by like certain vector A in Rm. So it's a vector in a ring where the ring is given by Zp of x quotient x to the n plus 1. So you treat these things as polynomials. and then you compute, call this function f indexed by a of a vector x of a vector z as a times z. Okay, and that basically, because a is a polynomial, it's kind of like if you're treating it as like product of two polynomials. Okay, and that ends up in a lattice point. Okay, and now, so what you do here is f of s, where f is one of these for a certain choice of a that you fix a priori. Okay, and then you choose here y at random from its own distribution y, and the norm of this y is going to be bigger than that of s, so that it hides it again. Okay, and then you compute the commitment again like f of y, same thing. So you can put it in like a polynomial in there, and commit that. Receive the challenge. Now the challenge will come from a distribution C. This is a vector, this is a vector. The challenge is going to be a single integer, or again, comes from a distribution, so it's like a coefficient anyway. Okay? And then when you compute the response, it's kind of like that one, right? It's going to be y plus cs. So you're taking your secret vector, which has like very low coefficients, you scale it up a bit, and then you cover it with y, right, which has bigger coefficients. And all in the end, you want this z to be still kind of small. Because if it's too big, then it's easy to forge. Remember that the situation for lattices is kind of similar that of codes, right? But in this case, what you want is the coefficients to be small rather than the Hamming weight to be low. Right? And you can control it much better because you don't have to worry about zeros and ones. You can take all the positions to be non-zero, but like essentially you see the coefficients, and then like a large part of the coefficient is going to come from the y, and a small part is going to come from the s. Okay, and that should be enough to drown the s into the y. Okay, so then you send this z, and essentially you accept. If what you verify is the same thing before, the f of z, when you put this into a lattice point, it should be y plus c times the public key. And you can see the verification is immediate, because all you're doing is computing a lattice point, so you're doing like a times y plus c, a times s. That should be, by transitivity property, like a times y plus s. So you can imagine that like multiplying by a in a ring is kind of like multiplying by a matrix where the rows are cyclic, like we discussed already this with cyclic codes.
Okay.
Right? So it's kind of like if you're computing a syndrome, if this was a cyclic code, but because it's like integers and stuff, it's actually like a cyclic lattice equivalent. Okay. Obviously, the reason why they do this with cyclic is that you don't need the entire. So to describe the entire lattice, you don't need the entire thing, but you just need the one row, right? You just need the one A, so that's how you can describe things compactly. But in principle, this works for like, you can say this is like in any lattice, okay? And then you also have to check that Z is in a certain G to the M, which is, the correct magnitude of the components, okay? Similar to like what you were doing before, you were checking that the Hamming weight was in the proper sphere. Okay, so now this works very well. Lubachevsky has also some interesting improvements. For example, rather than trying to control exactly the weight of z, what you can do is like because you drop these things at random, you can relax the parameters a bit, so that instead of being guaranteed that is in that g, it may be that with small probability it goes over, that like one or two of the components go over. So here you basically like abort if z is not in GM. And so you can try to sign, so you can really push, like there's an optimized thing, like if you say I have to try 2 or 3 times, or 10 times or whatever, with a small probability, I get out of the correct distribution, then I just try to sign again. But this helps relaxing the parameters a bit, because to be absolute, it's kind of like when you say like, oh, with a small chance this number is not prime. It would be a lot more complex to be like absolutely sure that the number is prime, right? It's not worth it. So here's the thing: is like we put this abort technique to make sure that like you can choose things at random, so that facilitates your proving that the thing is zero knowledge. Because if you chose them like fine-tuned, then maybe like you were trying too hard. So you just choose things at random, and with like really good probability, you're gonna end up where you need to end up. And if it doesn't work, then you just
information.
huh?
Does the abort leak information?
In principle, no. The abort is good for actually getting the zero knowledge, because you're just choosing things at random, and that means that you're not restricting yourself too much. Okay. And so this kind of protocol works better with lattices than with codes, because if you were trying to do the same thing here, you would have to have S of like very low Hamming weight, and Y to have like somewhat low Hamming weight, but it's a little bit more like discrete in a sense, the code base case. So you have like a lot of ones and zeros, and in the end you still kind of want this Z to be somewhere that is recognizable. So in the Hamming case, you would have to have this like still kind of like below the GV bound, where it's like uniquely decodable, or around that bound, and there's still a lot of zeros there. So in the end, that does leak thing, because you can look at the zeros, and if you look at many signatures, remember, we're trying to get something that is UF-CMA. I can always imagine that anyone can look at many signatures, and if you see a zero in a position several times, well, then that's kind of probably a zero anyway in the private key, right?
Yeah.
Whereas here, you're gonna see a bunch of vectors that are like, yes, like rather small components, but you never know, because you see like the integer eats up, you're summing a small integer with a very small integer, right? You're summing an integer between 0 and 100 with an integer between -3 and 3, okay? So that's kind of like a good example. Okay, yes, take your Y to be like between -100 and 100, and the other guy to be between -3 and 3. That's kind of the proportion. Then of course the final result is going to be between -100 and 100 with very high probability, unless the Y was like 98 and the S was 3, then you end up in 101. Right? And then they're like, wrong distribution, abort, try to sign again. Right? So, but most of the times what you see is between -100 and 100, and you can't really tell what the S was from that. Could have been anything, right? But the S is so much smaller, then it's eaten up by the distribution of the Y. And that is much better. So this is where, for example, lattices and codes behave differently, because they have a different metric, and in certain cases, the Hamming metric is good. In certain cases, the Hamming metric, in this case, the Hamming metric is not good, because it's just based on, if you type the same thing, S has like 10 ones, and Y has 100 ones. In the end, you're gonna have 100 and up to 110 ones, but the vector is still like 1,000 long, so there's like a lot of zeros, right? And you can still kind of eventually like do some sort of statistical analysis, figure out where the zeros and the ones are. So it's a lot weaker than that. With lattices, this works very well. It gives extremely compact signatures with very fast signing times. And this actually leads, so this is like, of course, a blueprint, right? Because this is an identification scheme. Then it needs to be turned into a signature scheme, and then it gets tweaked and improved with all the protocol stuff. But this is now one of the major candidates in the NIST process for standardization. So it's potentially the best lattice signature out there, and the base of it is this. It's definitely an interesting idea. Okay, so I think this is all. Well, not nearly all as I wanted to say, but for now, yes.